All right, so now that question time is over, let us go continue back for our lesson. So I've been kind of building up this lesson. Oh, by the way, the repo should be up to date now, at least to what we've had so far. So you can kind of follow along with like the lesson part, and we just add different sections. So we talked about a bunch of hypothesis testing. We got all the way down to here, basically, with students' test versus Welch's test, right? And basically, if you have to choose which one of them, which one would you use? I see Welch's. Good. Yeah, and why do we use Welch's versus students' t-test? At least, why do I suggest using Welch's?
Because it's more conservative, so
Yeah,
we're
right.
less likely to get an error. Which error? False positive?
That's right. So
Yes.
we're less likely to get a false positive error. Basically, if we do this, we're really, really certain. At least, in the terms of like, we are really, really certain. We're more certain than a student's t-test. We're less likely to make those errors. Can you still make errors? Yeah. But what's nice about Welch's t-test too is that people say like, well, should I use a student's t-test or a Welch's t-test? Basically, the reason why you'd want to use one that's more conservative is because you're assuming less. So you're putting less assumptions. For example, the assumption, what's the biggest assumption difference between students' t-tests and a Welch's t-test? What's the big assumption difference?
The difference in variances?
That's right. And specifically, what about the variance between students' t-tests and Welch's?
I think the variance of the t-test is 0.
Yeah, so the students' t-tests, they're both t-tests, right? But I think you meant the students' t-tests. Yeah, the students' t-tests, you assume that the difference between the variances are the same. So the difference between those, I'm sorry, the difference between the variances are 0. So there's no difference between the variance. Welch's t-test doesn't put that assumption there, which is why we have to make that correction factor that we just went over on the little question and everything. Okay, good. So just things to consider. All right, and so today we're going to talk about a little bit multiple comparisons. So I think I'm going to talk about this part right here about like not the danger, but like the warnings of multiple comparisons, like what we have to do. And then we can talk about ANOVA, which is meant to basically look at multiple, looking at multiple groups and trying to compare them at once. Okay. So multiple comparisons. So some of this stuff is also from the curriculum. So just kind of know that you'll probably see some of these familiar stuff. I'm kind of summarizing it more or less. Sorry, sometimes the equations get all messed up. So it's great. Wikipedia is amazing. Again, like for a lot of for technical stuff too. There's some great information about like multiple comparisons, the issues with this, how things are done, like different suggestions people do and stuff like this. One in particular, this is a good one. This is kind of mixed with like correlation versus causation, but you can see here, like they have a little example, letters in winning word of Scripps National Spelling Bee. So number of letters and the number of people killed by venomous spiders. And you can see a perfect correlation. So maybe we need to, for the sake of people who are being killed by spiders, we need to make sure that last word that they're going to do in the spelling bee has to be as small as possible, right? Yeah, like obviously, like that's ridiculous, right? This has no effect. But the big reason why you can actually build this up is by basically looking at many, many different factors. And eventually, by looking at enough things, just by pure chance, you will eventually find, what's it called? You will find relationships that don't actually exist, but they look like they're correlated together. And so that's the danger of multiple comparisons, is that as you compare more and more things, the likelihood of you basically looking at a relationship that doesn't actually exist becomes higher because you just are looking at more things. So that's the big thing we want to avoid with multiple comparisons. So basically, like our issues here, kind of just reading off of here, right? We're more likely to catch false positives, right? Is that as you test more, you're just more likely to find, cases where you say, oh, it is significant, right? Where where we reject the null hypothesis, but the null hypothesis is actually, well, we should say we should fail to reject the null hypothesis. That makes sense? Okay, and then remember that's our false positive or type 1 error. This is what alpha is represented by. So what can we do? Well, there's a few things we can do. So one option is the Bonferroni, I can never pronounce this right, Bonferroni correction. And again, Wikipedia is great at talking about this, but basically it's saying, hey, we have a bunch of issues with alpha. Like basically it's like as we test more and more, our significance level is not sufficient enough because we're going to get that 5%. 5% of the time we're going to make a false positive claim. So what we do, we just make alpha smaller. And so what we basically are doing with the Bonferroni correction is basically dividing alpha by the number of comparisons. So it's just like, why the number of comparisons? Because it makes it smaller. That's really all it really comes down to. You can actually work out the mathematics and say like, how robust this is. And it turns out it's actually pretty good. But this is like really, really conservative. Like, it's really unlikely you to pass a test. And this is why in practice, this is not usually used in like industry and stuff like that, because it's like, yeah, it's like you'll never make a false positive, but you'll keep making type 2 errors, basically false negatives, right? You'll keep basically rejecting or failing to reject the null hypothesis when you should have rejected it. And that's not great because you're like, hey, like how great of an experiment do we have to do? In some cases, this makes a lot of sense. Like I kind of brought up like particle physics. Particle physics basically has essentially this guy right here. Their alpha is very, very small because they do many, many experiments per second. And so they need to make sure that basically that what they see is real versus having like having a false positive. Okay. So one solution is like another method, the holm-bonferroni method, which basically you change the p-value, but you not change the p-value, you change the alpha value, and you just make sure the p-value that you're looking at has to be bigger than a certain value. So I wrote the steps here, but I'm going to be honest with you guys. No one does this. I should say no one does this, but like in practice, I don't know too many people who really like take this into account. In general, if you determine your significance ahead of time, and if it's really significant, maybe you investigate further. But this is a nice way to approach hypothesis testing. But basically the main thing here is I'm not even gonna go through this because last time I went through this with someone, they just like, their head was spinning like what? But basically the idea here is that you essentially sort your different p-values and then you basically use those p-values and compare it by, instead of like a really, really small alpha. So like remember the Bonferroni, you have to divide alpha and divide it really, really small. So imagine now you like the jelly bean situation where you have like different colored jelly beans and you have different p-values for each of those colored jelly beans, is that you basically sort, well, what's the most significant, or like what's the largest p-value in there? And you lead those up from like most significant to least significant, right? And then basically you say, okay, if it's really significant, right, like very, very small p-value, then you don't need to, you don't have to worry about alpha too much because it's like, oh, it's like 0.000001. You're like, okay, that's going to pass no matter what. So, and then you move on to the next one. But as you look at more and more, you basically adjust alpha to smaller and smaller. So that way, you know that it's going to, you're not going to accept something, or actually you shouldn't fail to reject something that really shouldn't be. Hopefully that kind of makes sense. So it's kind of like going the other direction. But the idea here is that this basically says, okay, we are perfectly fine with failing to rejecting when it's a very, very small p-value. But as the p-value gets bigger and bigger, we're going to basically keep adjusting alpha to try to keep up with the number of comparisons we're doing. Okay. Cool. The reasons why we do this mathematically, again, this is more like for all like, if you go into like a master's or even PhD, like in statistics, is when stuff you kind of talk about. Basically, this test becomes uniformly more powerful. Like for basically, there's more power to it. Like when we talk about like statistical power. So it actually turns out it's uniformly more powerful, which is kind of a big deal in statistics, but in reality, we don't really worry about it. And it's relatively simple. I know it sounds kind of complicated, but it's actually something you can kind of code up, like actually make it do this thing. And it's not too bad to do. Plus, what's nice about it is, like I said, a little closed testing procedure, which is a nice little math thing, but we don't need to worry about that. Okay. So main thing know about multiple comparisons, like, hey, if we do multiple comparisons, like basically try to do a bunch of t-tests on like different values that don't actually have an effect, you might actually find something significant. Okay. Cool. And there's some ways to do this. And one of those ways is going to be ANOVA. So let's talk about ANOVA.